Welcome to Get Your FRQ On. Today's video is on the 1998 exam, AB, question number 6, which is a calculator active question. The first part of the question, we're giving an implicitly defined function in x and y, and we are asked to verify dy dx. To do this, we're going to take the equation involving x and y and use implicit differentiation techniques, which is an application of the chain rule, to find an expression for dy dx. So we differentiate both sides implicitly and then solve for dy dx. If we do that to the given equation, we take the derivative of that equation using multiple differentiation rules. We get 6y squared times dy dx plus 6 times the group 2xy plus x squared dy dx. Keep in mind this 6x squared y, that's going to be an application of your product rule. And then minus 24x plus 6 dy dx equals 0. And we're going to collect our like terms with dy dx and hopefully be able to solve for dy dx to get an expression, specifically the one indicated in the question stem. So we gather our like terms, 6y squared dy dx plus 12xy plus 6x squared dy dx minus 24x plus 6 dy dx. Notice we distributed the 6 over the group, continuing to try to solve for dy dx. dy dx times 6y squared plus 6x squared plus 6 equals 24x minus 12xy. Divide both sides by 6y squared plus 6x squared plus 6 and factor out a 6 and we get 4x minus 2xy all over y squared plus x squared plus 1, which is the dy dx we are intended to find. So we have verified dy dx for the given implicitly defined function. For the second part of the question, we are asked to write the equation of each of the horizontal tangent lines. Now remember, the horizontal tangent line means that the slope of the tangent line will be 0. Well, we've just found an expression for dy dx, so what we're really interested in is when is dy dx equal to 0, so we can determine when the tangent is horizontal. So we take our expression for dy dx and we set it equal to 0. Notice that the denominator y squared plus x squared plus 1 is always positive. Since y squared is always positive, x squared is always positive, and adding 1 is certainly always positive, the denominator is never negative and it's never 0. So the only zeros of this expression must occur when the numerator is 0. So we solve 4x minus 2xy equals 0. Factoring out a 2x, we get 2x times 2 minus y equals 0. So either x equals 0 or y is equal to 2. Those would be our two options for a horizontal tangent line. If we start by assuming that x is 0 and substitute x equals 0 into the original implicitly defined function, we get a new function, 2y cubed plus 6y equals 1, and we need to know when that equation is true. Because this is a calculator active question, we can graph the function 2y cubed plus 6y minus 1, find its x-intercept, and we are allowed to use the decimal for our answer for this part of the question. So we have one horizontal tangent line with equation y equals 0.165. If we use the other possibility, y equals 2, and we substitute y equals 2 back into the original implicitly defined function, we get the equation 16 plus 12x squared minus 12x squared plus 12 equals 1. Notice that the 12x squareds cancel out, and we get 28 equals 1, which is never true. This gives us a contradiction. And so what this tells us is that there is not going to be a horizontal tangent line when y is equal to 2, because that derivative expression, whenever y is equal to 2, will never be 0. And so there is only one horizontal tangent line, and its equation is y equals 0.165. The third part of this question asks us to find a point x comma y such that y equals negative x, that is the line y equals negative x, is tangent to the curve. So this one's a bit tricky. So since this point must be on both the curve and y equals negative x, we substitute y equals negative x into the equation for dy dx and simultaneously set dy dx equal to negative 1. The reason we do this is we need the slope of the tangent line to the curve to be negative 1, but we also need to make sure that that happens at some point where x and y are opposites. It may very well happen somewhere else on the curve, that some other point has a tangent with slope negative 1, but it might not happen at a point where y is equal to the opposite of x. So we have to substitute both of those things into the equation for dy dx. So substituting negative x in for y and setting the entire expression equal to negative 1, we get 4x plus 2x squared equals negative 2x squared minus 1. If I set that all equal to 0, I get a nice quadratic equation. 4x squared plus 4x plus 1 is equal to 0. That's factorable. You can use the quadratic formula, whatever your preferred method for solving quadratic equations is. In any event, the solution that we're looking for is x equals negative 1/2 and y equals positive 1/2.